go. I'll point out that I'm wearing everyone's favorite sweater today, in case you hadn't noticed. All right, so recording, it's gonna get weird. Here we go. We wanna do, so here, this is going back to, I wanna say chapter 2, right? So here, this is from chapter 2. Oops. Might be helpful, right? And so we want to find the Cartesian product, and we did a few, but we didn't spend a ton of time on it. So M is it's kind of a weird setup, but I wanted to kind of give you a harder problem than what's on the final. So here, the distinct letters in mathematics. So what I'm going to do first is I'm going to figure out what the set M is, and then what the set B is. Hey, why is it B? I don't know. I stole it from somewhere else, from an old final. So, all right. So let's figure out what M is. M is the distinct letters in the word mathematics. So it's going to be M-A-T-H-E, mathematics, right? So first of all, right, the second M is already taken care of, the second A is already taken care of, the second and T is taken care of, and then X. Okay, do the same thing for B. Haha. Let's call this N. My first typo. No wonder, probably didn't make sense. Probably not the first, or sorry, it is the first typo, probably not the last, very unlikely. So my apologies. N. I should change that right now, but another list. Question 2a. B equals N. Okay. Distinct letters in nevertheless. Oops. N, E, V. E is already taken care of. R, T, H. E is already taken care of. L, E is already taken care of, and S. And then S is already taken care of. Okay. So the Cartesian product, M by N. So M times N, we set it up as a table, and then we have to figure out all the different combinations of M by N. So M has to be the first thing that goes in there, and N has to be the second thing that goes in there. And then we just match these up. So if we have, oh, hey, what happened? Undo. No, I wanna, okay. So what we do is we have M-A-T-H-E-I-C-S. Okay. So this here is M. And then nevertheless, N-E-V-R-T-H-L-S. This is the set N. Okay. So now we're going to make, and it's going to be large, right? We're going to make combinations of M by N going through each of these rows and columns. Right? So we have MN, ME, MV, MR, MT, I need more space, yikes. MH, ML, and MS. Okay. I'm gonna do this next row here, AN, and then I'm gonna do ... and cheat because it is in the solutions that I just posted. So AE, AV, oops, AR, AT, AH, AL, AS, etc. Okay. So this, right, this is from your M, and the second term in the coordinates, it's all coming back. The second coordinate is from the second set. What's the cardinality of M by N? So the cardinality is how many things are in there, how many things are in the set. And so each coordinate is going to be one element, right? So MN, ME, that's 2 elements. And so what we have here is 1, 2, 3, 4, 5, 6, 7, 8 by 1, 2, 3, 4, 5, 6, 7, 8. 8 by 8 is going to be 64. September does feel like an eternity ago. Let's say half an eternity. Eight by 8, or I should do it proper. The cardinality of M by N is 8 by 8, so 64. We should be precise. Okay. Is the set M by N, so now remember, you're going back here and you're thinking about, okay, well, M by N, is it the same as the set N by M? No, right? Because remember here, this first element comes from the M and the second element comes from the N. So if we flip these, right, this first term would be NM, right? And there is no such term in M by N, right? So here, for 3, consider M by N from I, and now consider N by M, right? Which is going to be something like, I guess I should write it out. Nevertheless. 1, 2, 3, 4, 5, 6, 7, 8. Got them all. Got to catch them all. Oops, need a little bit more room. Mathematics. Make sure I got all 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, great. So now if I think about this, this set, this is going to be NM, NA, NT, NH. Oops. There should be commas between these, but because we're setting it up as a grid, I can ignore them. But if you're listing them in a set, then each of these elements should be kind of separated by commas, right? Comma, 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 comma. But NH, NE, NI, oops, NC, and NS. So we see that M by N is not equal to N, oops, by M, right? Because order matters. because I shouldn't say order matters, because the order inside here doesn't matter, right? Because it's, well, maybe it does. It's a coordinate pair. Zach asks, I was curious what sort of work you would want shown for 3. So you could do a specific case, right? In n by m, you have a point nm, which doesn't exist in m by n. So you could say something like that. So here, I'm going to ditch this because I kind of talked myself into a hole. Or you can argue, since n by m yields a point, so you could just drill it down to 1 point, nm, which does not exist in m by n, we see that n by m does not equal m by n. Yeah, so we call it a proof by contradiction. So you just have to find one case where what you're trying to prove is true, or kind of not true, I guess, where they're not equal to each other, and then that would kind of moot the whole idea, right? So because we're able to find this point nm, now let me see if there's, because both of them have t's and both of them have e's, so there are points that are going to be the same, but not all points are going to be the same, right? So you just need to find that one point that doesn't exist in from both, right? If that makes sense. And then finally, is the cardinality of m by n the same as the cardinality of n by m? Yes. All right. They don't have to have the same number of elements, they just happen to. So the fourth part, yes. Since the cardinality of m by n is 8 by 8, and I'm going to do this kind of like a joint statement. So here, m by n is equal to 8 by 8, which is also equal to n by m, the cardinality. Right, so I've got this kind of go-between where they're both equal to 8 by 8, and then I'm able to say, well, can't remember what that law is called, but probably something like transitivity. So if m by n is equal to n by m through this 8 by 8, then they're the same. Yeah, exactly. Okay. Cool. All right. Any questions about that one before we go on to 6? I'll go grab 6. I'm guessing 6 from the long answer. And I think it was it? Great. Yeah, awesome. Okay, I'll grab this one. Oh yeah, so I kept this one in here because it's actually quite a bit easier than what we did, but we didn't actually do anything like this. So I'm glad you brought this one up. But you'll see that it's quite a bit easier than what we were doing. Okay, so the key here is that when we're given the coordinates of the function, right, we know that a function, so each input can only give one output, right? An output can come from multiple inputs, right, but not the other way around, but not to be one-to-one. Anyways, I'm getting ahead of myself. Anyways, so here, what this thing is saying, so if we have, if f is equal to the set of 0, -2, 2, 0, 4, 6, and 6, 2, what this is saying is that this means that f of 0 is -2, okay? So if I give it 0, it gives a -2. So the output is -2 and the input is 0. And if we're talking about the inverse, right, the inverse of -2, so essentially if I move this f over to the right-hand side in kind of a fake way, then the f inverse of -2 equals 0. Oops. Okay. So what you can do is you can take each point and kind of move around the functions. So here, let's start with A, f composed with f of 2. Okay. So if we rewrite this like we were rewriting things, this is the same as f of 2. Okay. Right, instead of x, so we've been doing the general x, so that's where I have to take the function and put it inside, right? So now, right, what I'm doing is, looks like we had a eureka moment. That's great. I'll keep going. So here, f of 2, I can replace that with a 0, right? F of 2 equals 0. So what we have, we can write is f of 0, but f of 0 is -2, right, from here. So you can kind of use it as like a chain, I guess, to kind of go all around this thing. So let's go through all of these just so that we have them. But you use the same idea, right? F of 4 is going into the function g, so f of 4 is 6. So now I'm taking g of 6. G of 6 is 5. Right. So let's see here. B, g of f of 4 is g with f of 4 inside. So g f of 4 is 6. G of 6 is 5. I think I'm missing it. No, it's all there. Okay. I'll go through the next two, but and even D is fine, right? As long as you kind of recognize that if you're doing the inverse, you're going from the output to the input, right? So you're kind of moving backwards. I want to work up to E and F because those are a little bit weird, but we can especially talk about E. Talk about E. Okay, G of 0. Oops, sorry, G composed with G. But I just read it as G of G, which it is. G of 0. G of 0 is 3, and G of 3 is 8. But I will write out my steps here, G of 3 and 8. All right, so for showing your work, I want to see this middle step, right? Especially in case you got it wrong or whatever, then I can still give you part marks. Whereas if you just jump to the answer, then I can't give you any marks. D, G inverse of 8. G inverse of 8. So now I have an output of 8, and the inverse of that is 3. That one doesn't need any work. E, F composed with the inverse of F of 2. Yeah. We can tell from the function f that it is 1-to-1, right? Each input only gives one output, and each output only comes from one input, right? And so because f is 1-to-1, we know from that inverse property that f composed with its inverse of x should equal x, right? And so I'm expecting this to be 2. I'm just going to follow through. But you can kind of talk your way through it, right? If it's 1-to-1, I know that that inverse property is true. So f composed with the inverse of 2. Okie dokie. The inverse of f inverse of 2 is 6. Okay? And then f of 6 is 2. F of 6, which is 2. Okay. Since f is 1-to-1, we know the inverse property is true, or inverse property holds. F composed with its inverse of x should equal x. And then lastly, G composed with F composed with G. Now we only went to 2, but you can easily extend it, right? You're just stuffing G into F, F of G into G, right? And so you're just going to keep stuffing this thing. G composed with F composed with G of 4 is G of F of G of 4. 1, 2, 3, there. Finish all your brackets. So G of 4 is 2. Okay, so I'll start there. Which is G of F of, I lost it. I think it's 2. Yeah. And then F of 2 is 0. And G of 0 is 3. Oops, sorry, 3. Just plain 3. There's some other questions here that we could ask, right? So you always want to, when you're studying, you don't just want to study the questions that I've given you explicitly. You want to kind of challenge yourself to think about other questions that could be asked about this thing, right? So what are some things that we've asked in the past? Well, on test 2, I want to say, right? I gave you something like this, and I asked you, hey, is it 1-to-1? Is it on 2? Right? So you could talk about those things. Right here, we've done a lot of work with this one, so I'm going to move on. But it is 1-to-1, right? Both of these are 1-to-1 because each input maps to each output or individual outputs for both of these. Just making sure. Yeah. And then without the set that it's mapping to, we can't tell if it's onto, right? But that's something to know on its own, right? Okay. Hey, that's always a good feeling, right? When it's easier than you thought it would be. Yeah, cool. Should we do some of those Boolean algebra questions? I might have missed your requests if there was some other requests here, but we've got our work cut out for us, so. Let's do 18. Copy. Okay, so here I'm working in X, Y, Z, right? And so to find my disjunctive normal form, first of all, if I have to write F in terms of the logical statement with connectives, I can do that, right? In fact, let's just kind of, I'm not going to ask you this on the final, but I mean, there's no harm in covering it in the review. So here, I'll say A, not on the final. But I can rewrite f of x, y, z is x and y, or x and not z. So this is the same as x and y, or x and z bar, or z prime if you prefer. Okay. Those mean the same thing. Okay, so we didn't talk about that, but just remembering that multiplication is and adding is or, you can easily do that question. Let's do B. I did it in kind of a muted color because it's not on the final. I want all my answers to stand out this time, so I'm using light blue. Okay. Find the disjunctive normal form of f expressed as a sum of the midterms. Okay, so remember how we did that? We said, okay, well, each of these terms has to have an x, a y, and a z, right, in some form, right? And so we use that trick of multiplying by 1, using the fact that if we're missing a z, then z plus z naught, or not z, is equal to 1. So I can multiply by z plus not z. So here's what that looks like. F of x, y, z is x, y. And then here, I'll just denote that I'm missing a z component first. Plus x, and then here I'll show that I'm missing a y component. Z prime. Okay, so here I have x, y times z plus z prime. Let's use the primes. I don't know which you prefer, but it doesn't matter. Just be flexible. And then x times y plus y prime, z prime. Don't make that same mistake that I did in the notes earlier, right, where I bumped this z prime over to the left-hand side to make my multiplication easier, but then I had them in the wrong order, so it kind of made it hard to find the binary. So I'm just going to keep it in the middle. You can bump it over, just remember the order x, y, z for your binary code later. Okay, so this becomes x, y, z plus x, y, z prime plus x, y, z prime plus x, y prime, z prime. Not bad, right? We've seen some nasty ones, so this one's not bad. You want to look through and make sure you don't have any duplicates like here, right? Because these can be lumped as one, right? Remember, f plus f equals f, right? So this function, if it's the same as this function, I can lump it together and summarize it by one of those. Okay. XYZ prime plus XYZ prime is XYZ prime. I want to make sure that I did that. Yep, looks good. Okay. So my DNF then is XYZ plus XYZ prime plus XY prime Z prime. This is the DNF. This is the disjunctive normal form. This is the DNF of f of x, y, z. Now express the disjunctive normal form, the DNF of f, in the sum of the min terms shorthand. Okay, so what I need to do is I need to convert these to binaries, right? And so here, let's see here. F of x, y, z is x, y, z, just rewriting it out here, x, y, z prime plus x, y prime, z prime. Okay. So now, right, in my binary here, I have 1, 1, 1 and 1, 1, 0 and 1, 0, 0. This is why the order of my x, y, z matters so much, right? Because 1, 1, 0 is different from 1, 0, 1, for example. Right? And so here, my label then is just converting this from binary to decimal. And so here I've got 1 plus 2 plus 4, so putting me at 7. Right? 1, 4, 6, 7. Okay, good. And with 3 variables, right, I know I go up to 7, so it makes sense. 1, 1, 1. Just want to check my work. 1, 1, 0. Okay, so 4 plus 2 is 6. And then 4 plus 0 plus 0 is 4. Awesome. So then the sum of the min terms, so f of x, y, z, in terms of the sum of the min terms is going to be, and we write them in order, right? 4, 6, 7. Okay, good. Now, so we've done that, and then construct the Karnaugh map. Do not circle or simplify. Okay, so just make the map, nothing crazier. Okay. With 3 variables, it's not bad, right? D, I think it's D. And C, I didn't label. There. The Karnaugh map. Okay, I've got X, and then I'm going to have Y, Z up top. X is either off or on, and then remember the order for Y, Z. You start with 0, 0, 0, 1, 1, 1, 1, 0, but that changes the labels. I mean, if you want, okay, you could have X prime here, X. So here, I'll just do this. X prime, X, Y prime, Z prime, Y prime, Z, Y, Z, Y, Z prime, right? And then you could just skip the labels and go straight to x, y, z. X, y, z is here, x, y, z. So you'd put a 1 here. I actually prefer the labels. I find that they're a little bit easier, especially if you remember 0, 1, 2, 3, 4, 5, 6, 7. Right? It's kind of fun to zip around like a little bee around here. So we've got 0, 1, 2, 3, 4, 5, 6, 7. We could simplify this, right? The tricky part is you'd have a group of 2 here, and you'd have a group of 2 here, right? Going all the way across, right? So it said don't simplify, right? But here would be 1, just for practice. I know I want to circle those so badly. Yeah, because I feel like I got really good at it. So why not? Why not? Let's do it. So here, let's figure out what this guy is. This is my first one, because it's kind of obvious, right? Jumping off the page at me. So the only thing, so here, x is being held steady, right? So x is on for both of these, and y is on, and z is switching back and forth. So we only keep the ones that are held steady, right? And so here, this is 1, which is x, y. Okay. And although it might be tempting to just circle the 1 on its own, we know we have to make these groups as large as possible, right? And so here we've got kind of this group here, which I'll call my group number 2. Now for this one, instead of the y held steady, now z naught, or not z, is being held steady, and the y is allowed to switch on and off. So, and still x is held on all the time. So this is going to be x, z prime. So therefore, f of x, y, z, we can rewrite as xy plus x z prime. Question 8, you got it. I'll put it on the list. I know, it feels weird. And if you guys want, I can ask you to do it, because now, once you kind of get the hang of it, it's like, okay, it's incomplete if you just did the map. Not asked to circle or simplify. But we're bad to the bone. Oh, is it the initial function? No wonder. Let's see here. Yep. You want to do the circling on the final? You got it. Oh, you don't like the exponentials, huh? All right. Well, that's good to know. I'll make sure you don't get back to the to the original function. That seems like a womp moment. Maybe that's why they didn't want you to circle it. But it's nice to know that we did it right? So kind of a nice way to check your work. Yeah, ditch an exponential and Let us do the circling. Yeah. Oh, we're too lazy to come up with a function. Okay, well, just don't let them circle it. Hold them off. Too funny. Okay, so we did say we were going to do both the Boolean function ones, but I feel like we did this one. Did we do this one in class last day? I feel like we did. It's not the same one. It's either on or it's off. That's Boolean algebra. For some, it's off. We didn't do this one in class. Let's just do it. Why not? I think I kind of, I feel like I did it, but I might have led you astray because you don't actually need to find those labels. So let me just go back to our notes from last day. And I think it was at the very, very end. Yeah, where we assumed it was the DNF. But actually, I want to do the other way. So I want to use this way instead. So in class, very end of December 7th, we solved this by converting to the binary labels. First. Now let's solve it another way, right? Just so you have some options for solving this thing, this massive thing, okay? So what you want to do is, first of all, you want to make up your map, right? So construct the Karnaugh map. Okay, fine. Let's see here. So what I'm going to do is we've got W, X, and Y, and Z. 1, 2, 3, 4. Okay. And then because I'm a creature of habit, I'm going to use my zeros and ones. Also, just to make sure, because I've got an internal rhythm, 0, 0, 0, 1, 1, 1, 0, 1. Or the other way around, 1, 0. When I see it, I'll know. So I am going to do this 0, 0, 0, 1, 1, 1, 1, 0. Right? And I'm going to do that inside for both of these here, 0, 0, 0, 1, 1, 1, 1, 0. Right? And just do enough of these to kind of have that in your mind, right? Or remember that this is the order that you have to go in. Okay, so now I'm going to translate these into W prime, X prime, Y prime, Z prime. Okay, so this. Oh. Tonight, unprecedented action taken by. Do you have a question, you think? Maybe not. I'm going to mention you. Maybe there. Okay, so I am going to write these out in terms of the literals. So W prime X prime, W prime X, W X, and W X prime. Okay, I want to make sure that I always loop back to here, right? So I have 2 where X is on in the middle, and then 2 where X is off on the outskirts. Okay. So far, so good. Y prime, Z prime, Y prime, Z, Y, Z, Y, Z prime. And again, I want to make sure that I kind of loop around. Okay, so what I'm going to do, instead of, I can easily convert these to the binary labels. And for me, that's the easier way to do it. But I understand that that's kind of a little bit of a longer way. So I get it if you don't want to do that. So here, what I need to do is I need to put a 1 in the box that corresponds to all the primes, right? And so here I've got W prime, X prime, Y prime, Z prime. So I put a 1 here. Okay. And what I'm going to do as I go is I'm going to cross these off just so I don't get any ideas and go back on 1 or something weird like that. WX prime, Y prime, Z prime. WX prime, Y prime, Z prime. W prime, X prime, okay, Y prime, Z. W prime, X prime, Y prime, Z. WX prime, Y prime, Z. WX prime, Y prime, Z. Yeah. W prime X, Y prime, Z prime. WX, Y prime, Z prime. W prime X, Y prime, Z. W prime X, Y prime, Z. Okay. Let's just check against the map that we had last day. No peeking at the groupings, but it looks the same, right? So either way, if you figured out what the labels are for each of these and then map them out according to their labels, or if you just took each term and mapped them out, then it's going to be the same. Okay, so this is the one that they're all groups of 4. Amazing. Incredible, right? Remembering that this thing is kind of, yeah, no peeking. Well, I think you have it in your notes anyway, so. So you have these obvious groups of 4 here, and also here. The less obvious group of 4 is the one that loops and kind of goes from the top to the bottom, or kind of the other way around. So remember, each of these are kind of revolving. Right, make a toilet paper roll. Oh, you know what? I just had a paper towel roll that I could use. Tempting. No. I can make all my groups just fine. I don't need a toilet paper roll. All right. Usually I use pink for my hardest grouping, so I'm going to change that to orange here. Orangey, glad I didn't say banana. There. I'll call this group 1. Group 1, right? If it spans a whole column or a whole row, then it's just summarized by the name of that column, right? And so here, this is going to be Y prime, Z prime, because it's allowed to change over W, right? Sometimes it's on, sometimes it's off. X is on, off, unpredictable. Only things held steady is Y prime, Z prime. So here, this is Y prime, Z prime. Okay. Kind of option number 2, or group number 2, is also a group of 4. Kind of my next obvious group here. Okay. So now I need to figure out which ones are held steady and which ones are switching on and off. I can get rid of those. And so here, W prime is being held steady. Okay, so that's great. X is on, it's off, or sorry, it's off, it's on, in that order. So I'm going to write down my W prime. And then moving on to my columns, it looks like my Y prime is held steady, blah, blah, and Z is off and on. And so W prime, Y prime. Now, my last one, right, we said, okay, there's this kind of tricky group where it loops around. And so what we're going to do, oops, like I said, I use pink for my hardest groupings, or I will use pink for my hardest groupings. So this one here is, what is it? All right, so here, W prime, W, so W is allowed to change, so that's out. X prime, so X prime is held steady. So that's my first literal going into this thing here. And then same thing across here, so Y prime, the whole thing is one big group and just Y prime. Except it's, this one's missing. This one doesn't have one, making a mess. Oh, so just as a, sorry, I didn't read the whole thing, Zach, sorry. If we also, yeah. Exactly. So if you had one here, then you could summarize it as all of Y prime. Good thought exercise. I should read the whole comment before I blab on. Good. So here I've got X prime, okay. And then Y prime is being held steady and Z is switching, so I've got Y prime. Okay, so then that means I kind of feel like this should just be one part, not two parts. It's kind of weird because then you'd have to do an empty map with all the ones and then redraw it again and then do their groupings. No, I'll just make it one thing. That was weird. So now we want to simplify this as much as possible. So f of w, x, y, and z is y prime z prime plus w prime y prime plus x prime y prime. Hey, they're all off. Something's a little off. Okay. Everything's a little off. Just a little off. Okay. So, let's see here. Question 8 was on request. Let me just, I'll be right back. I'm gonna stop this recording. Have a look at question 8 and then we'll go through it together. Let's see here. Maybe I should have a, oh yeah. Hey, that's great, Dermot. Had to check on the ETA of my lunch. Wonderful to have kitchen staff. All right, so let's see here. Okay, question 8. So we have two lines, right? We know that these are linear functions because there's just an x and a y, no powers, no nothing, right? And so I know that these are two linear functions. And I mean, it says that they're two lines, but it's just another kind of check-in point, right? Do I know what an equation of a line looks like? Yes, I do. It has to have an x and a y, and that's it, right? It doesn't even necessarily have to have an x, right? If it's a horizontal line, y equals 4, for example. Had to think about that one. Okay, so determine whether the lines are parallel, perpendicular, or neither. Okay, and so what we need to remember is that for two lines, okay, let's just write down here. So for two lines with slopes m subscript 1 and m2, right? The slope of the first line and the slope of the second line. They are parallel, right? Thinking about what it means to be parallel, well, it means they have the same slope but different intercepts, or possibly the same intercept, but that's not very interesting, right? If m1 is equal to m2, okay? They're going to be perpendicular, and there are two ways that we can check for lines being perpendicular. They are perpendicular, so like this at 90-degree angles. They are perpendicular if m1, sorry, I'm going to use m2. If m2 is the negative 1 over m1, okay? Or if it's easier, m1 times m2 is negative 1. Okay. Right, and you just get there by multiplying this m1 over here. m1 times m2 equals negative 1. So just, you only need to remember this one, or I guess this one if you want to divide by m1. But if neither of these are satisfied, then it's neither, right? You can have lines like this. They're not perpendicular or parallel. So most lines are neither, right? But we have to check, and how we check is through the slopes, okay? So what I'm going to do is I'm going to find the slope of this guy here. So for y equals 1/2 x plus 5, I'm going to say let m1 be the slope of this thing, right? The slope is always attached to the x once I've kind of simplified as much as possible. So here, m1 is 1 over 2. And then here, 2x plus 4y equals 7. I have to do a little bit of work to solve for y, right? So here I get 4y is 7 minus 2x. So y is 7 minus 2x divided by 4. So I get y is 7 over 4, right? I can split this up as long as I put both terms over 4, I can split it up. 7 minus 2x over 4. So y is 7 over 4 minus, or maybe I'll write 1/2 x. So then m2, I'm going to write as negative 1 over 2, right? Remembering that this negative here sticks with the slope, right? So what's attached to the slope? Negative 1/2. Or sorry, what's attached to the x? Negative 1/2. So now I have m1 and m2, right? I can tell that they're not the same, right? So they're not parallel. m1 is equal to 1/2, which is not equal to m2, which is equal to negative 1/2, right? Or maybe what I'll do is I'll kind of clean this up a little bit, which is not equal to -1/2, which is equal to M2. Right, kind of meet in the middle that they're not equal to. Therefore, not parallel. And here, you can do M2 and then do -1/M1 if you want, right? -1/1/2. Does it equal M2? No, it doesn't. I actually find that this way is easier. Either way, it's fine. M1 times M2 is 1/2 times -1/2, which I'm multiplying fractions, so I get 1 times 1, negative. -1/2 times 2, which is 4, which is not equal to -1, therefore not perpendicular. Does that make more sense? So it all hinges on knowing what it means for a line to, or for two lines to be parallel or perpendicular. But once you have those, you're just manipulating and finding the slopes and checking if they're equal or if they're the negative reciprocal. Okay. Good. Question 5. Oh yeah. Before we leave this one here, we can graph both of these. Can I cheat and use Desmos? I'm not going to get you to graph lines. Question 8. But let's check it in Desmos, just because we can. 1/2 x plus 5, and I feel like it was 2x plus 4y is equal to 7, something like that. If I did that right, or if I remembered it correctly, they are neither perpendicular nor parallel, which is exactly what we found. Cool. Question 5 then. Question 5, combinatorics, our favorite thing. No. I'll split it up because it's split across the page here. There. All right. Combinatorics. We thought we left this in the dust. All right. So a student number, if you think about a student number, we're allowed to have, so my number has 222 in it. I know, fancy, right? I think it's 300, I know how to type 300, 222, 379, something like that, right? So I'm allowed to have repeating numbers. And so that's going to be important to keep in mind for when we figure out how many possibilities we have. So for me, the easiest way to do this is just to have little spaces. So if we want 9-digit numbers, right? then what I do, I think the easiest way to do this, and there are a couple of ways that you can do it, fancier ways probably, but how I do it is I just make 9 slots. 1, 2, 3, 4, 5, 6, 7, 8, 9. Woof, so close. Okay. In each of these, I'm going to have the number of, well, digits that I can choose from, right? So the numbers I can choose from are 0, 1, 2, 3, all the way up to 9, right? Awesome. So I have 10 digits to choose from, right? Including 0. So for each of these, I have 10 numbers to choose from. Now, there's going to be some conditions here, right? So where the first digit is either a 3 or a 2 or an 8, sorry, a 3 or an 8. So now this first digit, I only have 2 choices, 3 or 8, right? So what I'm going to do is I'm going to write down 2 choices here. The rest of these, there are no conditions, and so I have 10 choices for each of these. Right? 10, 10, 10, 10, 10, 10, 10, 10. So you just want to make sure that you know how many choices I have for each of these numbers, and then what we do exactly what Riley did. You multiply them all out, right? And so you multiply these because you have to have, you've got 2 choices and 10 choices and 10 choices and 10 choices. So now we've seen that a bit more, right? Where we're saying, okay, well, if you're saying and, you're going to be multiplying, right? So we're going to multiply these. Multiply these, and so we get 2 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, which is quite large. I'm moving that 0, 2, 1, 2, 3, 4, 5, 6, 7, 8. Just make sure the decimal moves from here out 8, 1, 2, 3, 4. Oh, sorry, from here. 1. I was doing the negative direction. 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. Put some commas in here, multiples of 3 or groups of 3. So 200 million combinations. I think we can handle it. Got enough student numbers to choose from. Okay. So now we've got we've seen a few of these, or a lot of these, I would say. Suppose that we've got 15 women and 20 men. How many ways can we choose a president, a secretary, a treasurer, as well as a committee of 5 people? So now what we need to remember is if someone's chosen as president, for example, we're assuming they can't be chosen for a secretary as well as a treasurer as well, right? So if you're president, then that's where you are, right? You're not being chosen for the committee, you're not being chosen for secretary, so you're removed from the choices that you have there. Also, if you're on the committee, right, then you're on the committee, right? So that's a little bit different. So you're one of 5 people, and it doesn't matter the order there, and so it's slightly different. Okay. If Bob is president, Jane is secretary, and Joe is treasurer, that's a different grouping than Joe being president. Let's make Jane the secretary again. How sexist. And then Bob is the treasurer, but that's different, right? So we need to take that into account. So let's see here. What does this look like? All right. So here I've got a president. What's the easiest way to set this up, do you think? I've got 15 women and 20 men. So here, there's no mention of, okay, it has to be a female president and a male secretary, for example, right? So that could be an extra hurdle, right? But 15 and 20, so we have 35 people in general to start off with. So we have a total of 35 people, to choose from. Okay. All right. So if I have, and I'm just looking at, because I did do this one before, so how did I do it? And was I happy with how I did it? Yeah, I think so. So here, you have to choose a president, a secretary, and a treasurer. And a committee of 5. Remembering that, okay, so let's assume that we pick people in this order, right? So president, secretary, treasurer, we figure out who those people are first, and then whoever's remaining, we pick a group of 5 people. So here, the order matters. Right? Joe being president is different from Jane being president, right? And then the committee of 5 people here, order doesn't matter. A, B, C, D, E is the same as E, D, C, B, A. Impressive, right? Unless I screwed it up, I don't know. So we've got this kind of order matters and order doesn't matter, but together, right, we've got different combinations because for each committee of 5 people, right, we can have a different combination of president, secretary, treasurer. So if the order matters, this is a permutation. And if the order doesn't matter, that's a combination. And then I know it's hard when you're first kind of, or when it's been a while, or when you're not really used to working on these problems, to pick the and, right? Because she is a bad girl. Oh, she looked up. She's bossy, extra bossy today. So we have to have the president, secretary, treasurer, and a committee of 5 people. So if I were to say or here, then I'm either picking a president, secretary, and treasurer, or a committee of 5 people. That's not what I want, right? And so I know from this and that I'm going to be multiplying these two. I'm going to be multiplying the permutation and the combination. So here, although I totally understand that that's not obvious right away, but that's the logic. So here we're multiplying. So we've got from 35 people originally, right? I'm picking a group of 3 people where order matters. So I'm going to have 35 P3. And then here, I've extracted 3 people from that 35. So for the committee, I only have 32 to choose from, right? And so I have times 32, choose 5. Okay. Oh yeah, totally. So, yeah, because it would change it a little bit, Wyatt. Yeah, totally. So let's do that. That's a good idea. Stay tuned. So we've got 35p3, and I would probably just use your calculator. If you don't have a calculator, right, remember that npr is the same as n factorial over r factorial, or sorry, n minus r factorial. There. And ncr is n factorial over n minus r factorial r factorial. Okay. So if you don't have a calculator that does this on hand, then you would have to use the factorials, which could get a little nasty, especially because you've got 32, choose 5, so that's pretty large. Should we, okay, here. On your calculator, I'll do both. You've got 35p3, yeah, it's going to be 35 times 34 times 33. 35 times 34 times 33 is 39,270. Which I'll confirm with my buttons. 35p3, yeah, it's the same, good. And then 32, choose 5, I have 201,376. I multiply these, 39,270. 790, it's huge. Yeah, so you do need the final answer. 790,803,5520. By hand, sort of. 35p3 is 35 factorial over 35 minus 3 factorial. Times 32, choose 5 is 32 factorial over 32 minus 5 factorial, 5 factorial. Remember how to do these factorials if you have to do them by hand. I say by hand because I'm probably going to end up doing 35 times 34 times 33 on my calculator, right? So it's by hand, but not necessarily completely. So that's 35 times 34 times 33 times 32 factorial over 32 factorial. Hey, cool. Zach says it's almost exactly the Earth's current population. Crazy. Times 32, let's see here, 32 minus 5 is 27, so I have to go to 32 times 31 times 30 times, 29 times 28. 1, 2, 3, 4, 5 times 27. 27 factorial. Let's see here, 32, yeah. Over 27 factorial, 5 factorial. So the reason I wrote them out like this is so that I can cancel the 32 factorial and the 32 factorial. And the 27 factorial with the 27 factorial. Remembering that 5 factorial is just 5 times 4 times 3 times 2 times 1. So I have, it's still going to be a really nasty calculation. So that's what I mean by hand. I'm still going to have to do 35 times 34 times 33 times 32 times 31 times 30 times 29 times 28 over 5 times 4 times 3 times 2 times 1. But we can do it. And I'm just going to write it out here. 79080355520. Okay. So now, consider another problem that's not on here. So this is the one that Wyatt suggested. And let me just steal this here. So something where we're specifying the gender of all these, okay, because we've got 15 women to choose from and 20 men to choose from. I would probably approach this slightly differently. So let's say, I'll follow your lead here. If the president and the secretary, let's say, have to be women, and then the treasurer is allowed to be whatever. And the committee has to be, Okay. Why am I hesitating? How do we tackle? So if we're forcing this to be men, that's fine. If these guys have to be women, so the president and the secretary have to be women, the treasurer can be a man or can be a woman. How do we deal with that if we're having 5? You can tell that this is not, the problem is I wouldn't specify the committee. So I'm going to change it to be something more reasonable, something that I would expect you to be able to do. Let's change it to the treasurer has to be a man, and then the committee of 5 people. That's something I would expect you to do. Okay. So from 15, I have to pick a president and a secretary, right? But Jane being president and Sarah being secretary is different than Sarah being secretary and Jane being, no, it's not. Sarah being president and Jane being secretary, right? So the order matters here. And so, but it changes because I only have 15 to choose from, right? And so what I have here is I have 15P2. And it doesn't really matter here. There are a couple of ways I could do it, right? Because if I select just one in a permutation, then it is just going to be that number. But just for consistency, I'm going to have 20P1, right? Just 20 options, 20P1. If you do 20P1 on your calculator, you're going to get 20. So 20. Okay. But I'm just, so if you wanted to replace this with just 20, that's fine. I'm doing it to be consistent with what I did with the women. Okay. And then here, the committee of 5 people is, no, the committee can be anything. Okay? So here, I've used up 2 of the, oh, that doesn't sound good. Well, fine. So now, yeah, so 35 minus 3, so I've extracted 2 women and 1 man. It doesn't actually matter because I've taken out 3. And so 32, choose 5. You got it. So multiply these, right, times, and so I get 15, just using my calculator. P2 is 210 times 20 times, and then whatever this was, 201,376. Yeah, just show your work. So if you've done this then, and you go straight to here, I'm assuming you've used your calculator. If you don't have the calculator or a calculator, then you would have to use the factorials, but you would still probably want a calculator. So bring your calculator. Have a calculator. So this is going to be, I get 8, 4, and I might have flubbed it, so just check my work here. 8, 4, 5, 7, 7, 9, 2, 0, 0. Okay. All right. So let's move on to C. Unless there are questions, I'm keeping an eye, but sounds like you guys you got it. You flip a coin 4 times and keep a record of the results. In how many ways could you obtain at least 1 tail? So this at least problem, and I'm going to steal it so that I don't have to scroll back and forth here. Oops. So what I'm going to do is, again, I'm just going to make slots. Okay. And you could have made slots here as well, right? You could have done a slot for the president, a slot for the secretary, right? And so the first slot, you have 15. The next slot, you have 14 to choose from, right? And then the treasurer had to be a man. And so then you had 20 to choose from. And then the committee of 5 people, you'd have 5 slots. And then you would go from 32 to 31 to 30 to 29, 28. I think that's good. You'd end up at the same place, but sometimes I just find it's a little bit clearer to use permutations and combinations, but you can use slots for all of these, right? You have to be a little bit careful. How many do you have to choose from? So here, right, I'm going to flip a coin 4 times. I'll make my slots huge for some reason. That's okay. I only have 2 options, right? If I'm flipping a coin, I've got 2 options, 2 options, 2 options, 2 options. That's in total, right? So 2 times 2 times 2 times 2 is 2 to the power of 4, which is 16. So I have 16 different combinations that I can make if I'm flipping a coin 4 times. Now I have to have at least 1 tail. Exactly. Yeah, so this is at least 1. The easiest way to do that is to take away the options that don't satisfy the at least condition, right? So take away all combinations with no tails. Okay. You guys have this one under control. It's good. At least one. I know that's the tricky part. I mean, I'll show you another way that you can kind of like brute force this question if you really want to convince yourself, right? So I'll show you that. But so there's only one way to have no tails, right? That would be head, 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 right? There is only one way to get no tails, right? 1, 2, 3, 4, head, 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 which is 1 times 1 times 1 times 1. I don't know, it's always sunny in Philadelphia. Sounds like it's not true. So we've got 16. So therefore there are 16 minus 1, which is 15 ways to have at least one tail. Happy Sylvia, I don't know. Or you can, I'll say brute force this problem. Right? I'll have to check that out later. Flip number 1 can be either, and I should do these nice and wide because we're doing 4 flips, head or tail. Flip number 2, oops, can be either head or tail, right? Flip number 3, 1, 2, 3, 4, 5, 6, 7, 8. Head, tail, head, tail, head, tail, head, tail. Finally, flip number 4. Oops. Head, tail, 1, 2. I'll just do these. Got sloppy. It is a minimum spanning tree indeed. So, right, if I go through these, then there's one branch that gives me all heads. And then I can kind of trickle through all these branches to have at least one tail in each of these, right? So at least one tail. Here, no, yes, 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 yes. I don't know why I hesitated. I know there's only one that doesn't. All right, so in each of these, there's at least one tail as I kind of trickle down. Now I count how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 options. There is a slight probability that it lands on its on its side. But in stats, we just assume that that's not a possibility. and it's behind your ear. Then what? From your nose. Those are all options. But those options make our tree kind of nasty, so we're going to ignore those. All right. Let's see here. Hopefully that one's okay. Let's see here. Oh, yeah. How many arrangements, so distinct arrangements, what does at least one tail? It just means that you flipped a coin 4 times and you can have 1, 2, 3, or 4 tails, right? So the only one that's out is having 0 tails. So remember this one, how many, I'll say distinct arrangements because it's kind of understood, but how many distinct arrangements, just to kind of clarify, can be made with the letters from the word aposiopesis. I don't know. Is it even a word? Probably. Stole it. Again, it's from an old final exam, so I guess it's a word. All right. That's right, Dermot. Yeah, so if you have no tails, then that's not an option. Everything else goes. And so if you want to convince yourself with this kind of tree diagram, or it is a tree diagram, then you trickle down each of the paths and you check all the ones that have at least one tail. So how many distinct arrangements can we make? Remember these ones? First, you count how many letters there are. It doesn't matter how many duplicates. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters, right? Not distinct. And so here, let's see here. Aposiopesis has 11 letters, right? And so and then A is in there 1 time, P is in there 2 times, O is in there 2 times, S is in there 3 times, I is in there twice, O is already on here, P is already on here, E is on there once, S is already on there, I is already on there, S is already on there. Okay. So what we have to do is we have to take 11 factorial divided by, hey, no problem, Reed. See you on Friday. So we've got 11 factorial divided by 1 factorial times 2 factorial times 2 factorial times 3 factorial times 2 factorial times 1 factorial. You can ignore the 1 factorials, but I think it's easier to look at if I just have all of them in there. So I'm going to move this over a little bit here and have 11 factorial divided by 1 factorial, 2 factorial, 2 factorial, 3 factorial, 2 factorial, 1 factorial. Which puts me at, we've got 11 factorial. Most calculators have a factorial button, so you don't have to do 11 times 10 times, why am I blanking? 11 times 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1 is 11 factorial. I can't exactly cancel stuff because it looks like I have 3 factorial, but I'd still have to go to 3 factorial, so that doesn't help me very much. So I'm just going to use the 11 factorial button and find that this is 399,16800 divided by 2 times 2 times 3 times 2, right? Ignoring the 1 factorials because they're just ones. Divided by, and then I'll do 2 times 2 times 3 times 2 is 24. So this is 399,16800 divided by 24. Oh, I screwed up. 3 factorial. 3 factorial times 2 factorial. I'm just sorry. I should do that properly. I mucked it up. 1 times 2 times 1 times 2 times 1 times 3 times 2 times 1 times 2 times 1 times 1. So close. No, that's all right. I expected to go wrong at some point. But you guys, I expect to be flawless. How's that for a double standard? 2 times 2 times 3 times 2 times 2 is 48. 11 factorial divided by 48 is 831,600. How's that? So that's how many distinct arrangements there are of the words, or of the letters in the word aposiopesis. Weird. Okay. Awesome. The device of suddenly breaking off in speech. Wait, suddenly break the device. It's wild. Oof. And I know, Zach, I would probably say that it's like the hardest thing because you think you got it and then you feel like you have it under control and then you try another one and it's not the same. But I am trying to keep them nice and pretty reasonable, at least. So, and I can't wait to hear the pronunciation later. Apasiapesis. Wait. Apasai. Wow. Well, I screwed that up. All right. Well done, Zach. Well done. Stop talking about aposiopesis or else. Nice. Okay. If you guys have more questions, we can work through them. I don't have any other on request. Happy to go through more. I might go have lunch. 2H, you got it. If there are a lot of questions. If there aren't a lot of questions, we can just go through them. 2H. Yeah, what was I thinking? Scheduling this so that I couldn't eat. Anyways, foolish. Well, I wanted it to be kind of early in the day, but not too early. And then, anyways, yeah. It's hard to pick a time. Oh, yeah. So you have to solve for x in this thing. Okay. Is this the one you mean, Why? Cool. All right. So 2H. It doesn't need to be that big. All right. So, yeah, get everyone off on the right foot here. Yeah. Hey, that's a day's work in itself, getting up before noon. All right, so we've got the ln of e, which if you want to be sneaky about it, right, the ln, so ln is log base e of e, okay? So you can try it on your calculator, you're just gonna find that it's 1, right? So recall, ln of e is log base e of e. Okay, log base e of e is essentially saying e, so take the base of the log, e to the power of what equals e. Okay. Oh yeah, no problem. Yeah, you're welcome to come and go as you please. I'll post the video once we finish here. So awesome. So this is going to be, so e to the power of what equals e? Well, e to the power of 1 equals e. And so this is 1, since e to the power of 1 is e. Okay. So, oh, hey, Dermot, are you still here? Happy birthday! I totally forgot. Happy birthday. What a way to spend your birthday, right? Couldn't get any better. Downhill from here, I'm sure. All right. So back to logs. We've got basically 1. Yeah. 1 is the ln of root 2 over x minus 1. So I'm going to simplify this. So we get ln of e is the ln of root 2 over x minus the ln of e. So this is going to be 1 is the ln of root 2 over x minus 1. Okay. So I can move this minus 1 over to the left-hand side, so I get 1 plus 1, which is 2, is the ln of root 2 over x. Now, to shake this ln, I need to solve for the x, so I need to get it out of the log. And so to get rid of the natural log, I need to raise everything to the power of e. So e to the power of 2, remember you have to do it to both sides, e to the power of 2 is e to the power of ln of root 2 over x. And so you have e to the power of 2 is e to the ln of root 2 over x. Now the reason we did that is because these are going to drop out, right? This e to the power of 2 sticks around. So you have e to the power of 2 is root 2 over x, right? Because these two are essentially canceling each other out. And that's how you shake out that x from the log. Now to solve for x, I'm going to multiply x over here and divide each of the two over here. But I'll do it in 2 steps. You can do it in 1 if you want, but e to the power of 2x is root 2. So x is root 2 over e to the power of 2. Ta-da! And that's it. Because I think we had to just solve for x. And give the exact solution. So I have to keep this root 2 in the e to the power of 2. That's the exact solution. Cool. Yeah, totally. Logs, I feel like there's not a lot to logs. Once you've introduced the log laws, it's kind of like, now do it. So we didn't really spend a ton of time on logs, but they're so important. So that's why they come up quite a bit on the final. Good. Any other requests? Okay, well, I'm gonna pause it and then I'm gonna go have my lunch and then I'll be back. How about that? Eat that lunch. Back in action. So from test 2, whichever you want to call it, little fun quiz. Question 5. We're going to use log laws to combine and simplify as far as possible. That's the kicker here. So if we've got logs of the same base, yeah, I think so. I suspect that's what happens. So if I have logs of the same base, you know, you can hey, I think I did this. I think I read it as minus. I think. Let's do both. I might have to go back and remark that one if that's the case. I feel like oops. And someone's just bringing it up now. Come on. Let's see here. So I've got the log of y minus 4 plus the log of y plus 2. Could be because I'm sloppy. Let's see here. Logs of the same base, if I'm adding them, I can combine them by multiplying this out. So this is the same as the log of y minus 4 times y plus 2. Okay, which is the same as the ln of y squared plus 2y minus 4y minus 8, which is the ln of y squared minus 2y minus 8. I think I may have treated it as the log of y minus 4 minus the log of y plus 2 in my solutions. Where are those? You gotta wonder. I didn't. That is a relief. Okay. Looks like I did it like I should have. So that is good. So I don't need to remark it. But, right, so you want to show that you can combine these by multiplying inside. Exactly. So now if we try this one, just to have it under control, right, what this looks like is you have the same log here, but you're subtracting. So then, yeah, you divide inside. Y minus 4 divided by y plus 2. And there's nothing I can do to simplify that. If this was y squared minus 4, I could simplify it, but I can't in this case. No, it's all making sense, I guess. All right. Let's do B then. 8. I just read ln as log y minus log x minus 3 log z. Just who knows? All right, so for B, 8 log y minus the log of x minus 3 log z. The log laws say that I can move this coefficient from out front to the power of whatever is inside the log. So I'm allowed to do that. I'm allowed to move back and forth. And so I can rewrite this. My first step is going to be the log of y to the power of 8 minus the log of x minus the log of z to the power of 3. Right, I can move this power up front. Here, I've got minus 1 log x. If you prefer, you could, and that's where the division comes from, right? You could take this and say plus log x to the negative 1, right? Plus the log of z to the negative 3. You'll end up in the same place. So it just depends on which way you want to move. But in the end, we're going to end up in the same place. So I've got the natural log, natural log, natural log. So I'm allowed to combine these. But if I'm subtracting, right, y to the power of 8 minus the log of x minus the log of z to the 3. So if I'm subtracting, then I'm dividing inside that same log. So I get the log of y to the 8 divided by x times z to the power of 3. I combine these into 1, and in fact, just to show you where it came from, maybe I should not skip that step. I can rewrite this as log of y to the power of 8 minus, and then in brackets, the log of x plus the log of z to the power of 3, right? If I expand this negative inside, I haven't changed anything. Now I can simplify this a little bit, right? So this becomes the log of y to the 8 minus the log of x times z to the power of 3, right? Combining these because I'm adding, so I multiply inside. And then if I have the log minus a log, this becomes the log of y to the 8 divided by x z to the 3. A little bit better? Good. Well, you'll have a shot at redemption on the final. How about that? I think there's like 2 questions where you have to apply the log laws. It'll be very similar to the practice final. So however many there are on the practice final, how many to expect. Any other questions? Apply blah blah blah's law blogs. Blah laws. Law blog log laws. Exactly. If only we could make some sort of acronym for all the log laws inside blah blah blah's log laws. Wouldn't that be a feat? Bring the exponent down in front over, no, I can't do it. I'd be rich. If I can summarize the log laws in a funny acronym, no one pays for that. You guys are gonna crush the final. I know it. I do feel like you guys are gonna do really well. So I'm hoping for that. And no problem. Any other requests? Are you guys just feeling so good? Yeah, so you do have to find the inverse of a function. In fact, where is it on this this thing? Oh, here. Question. So it is just I don't think I put it. I actually swapped out a question that the other classes are doing for a function one because I felt like we worked on it more. So x squared. No, okay, so I didn't do it there. So the only time that I'm going to ask you to find the inverse, it looks like it's in the short answers, part D. Back to the practice final. To D. So let's do this one. We'll do part 1 and part 2 just for, why not? Okay. Show that f of x is 1 to 1. So to show that something is, a function is 1 to 1, remember we do f of a and set it equal to f of b. If we're able to cancel things and end up at a equals b, it is 1 to 1. Now, one thing that I want you to remember is that if I ask you to show me that it is 1 to 1, you need to end up at a equals b, right? And so no illegal math, nothing like that, just set up your 2 equations and work them out so that you get a equals b, right? And then you're going to find the inverse of this function. So for a, or I guess part 1, we're going to have f of a equals f of b. Okay, so what I'm going to do is 2a plus 5 divided by a minus 7 is 2b plus 5 divided by b minus 7. So what I need to do is I need to cross multiply and just kind of shift things around, and things will cancel out. And in the end, I'm going to end up at a equals b. Okay? So for me, I always just prefer to, and you have lots of options, right? But I prefer to just move this denominator over to the left-hand side and the right denominator over to the left denominator over to the right-hand side. And so I end up at 2a plus 5 times b minus 7 is 2b plus 5 times a minus 7. And like I said, there are a lot of different ways that you can do it, as long as you're applying all your kind of math laws properly. You should end up at a equals b. So expanding this thing and this right-hand side as well, I get 2ab minus 14a plus 5b minus 35 is 2ab minus 14b plus 5a minus 35. So what you can do, and my go-to is just shift everything over to the left-hand side, which makes the right-hand side 0, right? So that's kind of my go-to. Or you can kind of pick away things like 2ab, and then if you move this 2ab to the left-hand side, you'd end up at 2ab minus 2ab. So they would cancel out. Same thing with the 35. So you can kind of pick and choose values if you want. It doesn't matter. I like to move them all over, and as an exercise, let's just move them all over. See what happens. So I get 2ab minus 14a. So just rewriting the left-hand side, making sure you're all the way over to the left because you're going to need a lot of room. 14a plus 5b minus 35. And then you can either be really careful about changing each of these signs individually, or I'm going to have a minus here and then put everything, just kind of put it inside the brackets and then expand it out. That's being really, really cautious, but I don't want to mess this up and have to redo it, right? So kind of, you have to put in some time so you don't have to waste time redoing it. Minus 14b plus 5a minus 35, and then that's going to be equal to 0 because I've shifted everything over. All right, 2ab minus 14a. So now all I'm doing is expanding this negative inside, making sure I hit every term. 14a plus 5b minus 35 minus 2ab plus 14b minus 5a plus 35 is equal to 0. So now I'm going to cancel. Okay, so I've got some nice easy cancellations going on here. 2ab minus 2ab, great, they're gone. Notice I'm going to cross them off as I go because otherwise it can get really messy. So negative 35 plus 35, fine. And then I can collect like terms, right? I've got negative 14a minus 5a, so that's negative 19a, and then 5b plus 14b is plus 19b. So I get negative 19a plus 19b is equal to 0. Okay. I don't like dealing with negatives, so I'm just going to add 19a to the right-hand side. I know that puts me at b equals a, but that's the same as a equals b, so no harm, no foul. 19b is 19a. So if I divide this 19 over, then these guys will cancel, and I'm left with b equals a. So since f of a equal to f of b yields A equal to B, we know f of x is 1-to-1. Right, we've proven that it's 1-to-1 and therefore invertible. And therefore invertible. Right? So here I told you that it's 1-to-1, right? So now we know that we can find the inverse. So even if you're not sure how to do part 1, you can still do part 2 and just assume that it's 1-to-1 because I said show that it's 1-to-1. So even if you get stuck, right, just kind of pick up. And in general, that's kind of a good thing to keep in mind. So if there's something that you need from a previous part, because I know people have a hard time on tests when, you know, a part depends on a previous part, what I would want you to do is just say, hey, here's something that I know is reasonable for X, for example, and then just use that. I think any reasonable prof would follow through and make sure that you, as long as you manipulate things correctly, you can at least get some part marks. So just remember that in general for your schooling. So the hard part is knowing what's a reasonable thing that you can use in the place of what you should have found. But anyways, it's all a learning curve. So now we're going to find the inverse of f of x, 2x plus 5 over x minus 7. So 2x plus 5 over x minus 7. I'll just write out f of x is 2x plus 5. Of course, I've said it so many times now, I've forgotten. 2x plus 5 over x minus, okay. To find the inverse, we write y equals 2x plus 5 over x minus 7. You can skip that step if you want, but I'm going to do it. Y equals 2x plus 5 over x minus 7, right? So here, the step that I'm doing is write y equals f of x. Okay. The next step is you're going to swap your x's and y's. And this is the order that I prefer. Some people get you to solve for x. You're going to end up at the same place. So if you use the other order, that's totally fine. But I'm going to swap x's and y. There's only one y, but making multiples. So what I get is x is 2y plus 5 over y minus 7. Okay. So now I'm going to solve for y. So y, in this case, once I've solved for it, y is going to be the inverse of f of x. Okay. So once I have that y, that is my inverse. So here, first thing I need to do is I need to move this y minus 7 over to the x. It's going to get uglier before we can kind of simplify things, right? Because I want to get all my y's over to one side and just have one y. So this looks like x times y minus 7 is 2y plus 5. Okay. I can expand the x times y minus 7 as well as move this 2y, right? I'm trying to collect all my y's because that's what I'm trying to solve for. So I get xy minus 7x minus 2y is 5. Okay. This term has a y and this term has a y. So that's what I'm going to keep on the left-hand side. And then I'm going to add 7x to both sides, moving it over to the right-hand side. So I get xy minus 2y is 5 plus 7x. I can factor out a common y here. So I get y times x minus 2 is 5 plus 7x. So now, solving for y, all I have to do is divide both sides by x minus 2. So I get y must be 5 plus 7x divided by x minus 2. So therefore, f inverse of x, right? Notice that it's back in terms of x, but now it's the inverse, is 5 plus 7x over x minus 2. How can you check your work? Could use the inverse property, right? It's with a fraction like this, with an x in both the numerator and the denominator, it's a lot of work, or quite a bit of work, right? But if you take f composed with the inverse, you should end up at just x, right? Let me know if you want me to do that, or if there's a different question you want me to work on. Nice. 17C, what kind of work? Curiouser and curiouser. Let's see here. 17C, who knows? Oh, which of the following, oh, C. Oh, it's split across. Not really work. One thing, if you are writing it out on paper, so if you're not printing it, well, I guess I should mention that there's only 4 of you here, but just in general, I'll have a smushed together one in case you're not printing it and doing it on there. But if you want to print it and have like a real test sit down with spaces, I'll post one of those as well. So you'll have a couple to choose from. They're the same, obviously. So for this one, you would, so this is from 17C, you would need to copy out this tree, and then I would probably just circle them and kind of number your circles. There's not really work that you can show, right? But because that's what we do for the minimum spanning trees, right? I think I don't even really draw in a blank. That's the one where we circle the shortest ones until we've cut all the vertices, right? I think. Let me just check. It is. So what I would do is I would take, I would do 4, and I'd probably label them like this one. I know. Just want to chop off I mean, I'm sure that's some sort of algorithm as well. So you're not wrong. But in our case, we only start with the small ones and build up. Yeah, so I would probably do something like this. 1, correct me if I'm wrong, 2. And maybe what I'll do for my own kind of sanity, I'll highlight the vertices that I've already caught, because otherwise it makes it tricky, right? E and J. So then after this, it looks like I have 19. And I guess highlighting the vertices doesn't really do much because they still have to be connected, but let's just keep going. 19, 24, I think. Oh, and this would be 3, this would be 4. So I've connected here and here. Here and here. And 24, what's my next one? There's two 30s. I'm going to end up using both of them, I think. 5, 6, and then 40, 7, we're getting there. And then the last 40 gives me a minimum spanning tree, 8. Because now they're all connected, right? Going like this, but no circuits or cycles. Hey, check this out. Or maybe what I'll do is instead copy. Just to be safe, I would do it where you, I mean, I'd have to look it up to see if they are equivalent. I've only ever done it where you build up from the small ones. But that said, I haven't done this very much. So if your chopping method seems to work, then that's great. There's gotta be some reason why building up would be better. There is some kind of, with the 240s, for example, you would choose the one that's better. But I mean, that would be the same for your cutting one. Yeah, maybe, yeah, I don't know, with more circuits. Yeah, I don't know. You'd have to ask, like, do you guys have gym? Nassos? No? You will. Maybe he can tell you. I feel like he does this kind of stuff. I don't know who else. I mean, probably all of them. I only know, I think I only know Jim and shoot, his name's not coming. The other guy you have. What's his name? I don't know Sarah. I'm drawing a blank. Ken. I don't really know Alan, but I know Ken. He might know. Maybe Alan knows, I don't know. But I'm pretty sure Jim would be able to tell you. Awesome. Yeah, I only know Ken. He's a fun guy. Any other questions? So I hate to leave you hanging there, Zach, but I don't know. I don't know when it would fail. Probably never, because it seems to me like building up to a minimum tree and chopping down to a minimum tree should be the same. Exactly. But it wasn't addressed in the textbook, so that's why I don't know. That's the only exposure I have to it. So there's gotta be some reason, but Maybe they're just trying to keep it simple. What a good sport. You can do both. Why not? Same minimum spanning tree. Question 11, you got it. Oops, not that one, here. 11. Oh yeah. So a truth table, we've got P, Q, not P, and Q. So we need to figure out how many variables we have. We only have 2, right? Which means we have 4 different combinations, right? And so for a truth table, I'm going to set it up like this. P, Q, right? I'm going to start out, and I always start out with true, true, false, false, true, false, true, false. And then I'm going to build up these statements individually. So it looks like I need a not Q as well as a not P. So I'm going to do these in order. So I'm going to do not P is false, false, true, true, and not Q is false, true, false, true. I just find it's helpful to have each of them kind of lined up so that I can just look at them. So if I need to set up P and not Q, P and not Q, with the and, both of them have to be true for it to be a true statement. If there's a true and a false, well, then the overall statement is false. So, and it is just building a truth table. And then remembering that a tautology is when you end up with all true at the end, right? So you'd have to build your truth table first and then show that it is all true. So P and not Q. So I'm in this column and this column. So I'm going through and I've got true and false, which is false, true and true, which is true, false and false, which is false, and false and true, which is false. Not P or Q. So now just one of them has to be true in order to yield a true statement. So not P or Q. So now I'm here in not P or Q. So now I'm going between these guys, and I just need one true in order to make a true statement. So true and true or false is true, false or false is false, true or true is true, false or true is true. Okay. I have to do it one way, and then I should be able to go the other way as well. Now I have to remember, so I'm looking at this guy here, and I didn't leave myself enough room, of course, again. So P and not Q, going to not P or Q. Okay, I'm gonna have to actually flip back into my notes. Luckily, they're available to me. When did we do truth tables? So the only time that this is, it's in our notes right here, this is only false is if you're going from a true to a false statement. Okay, so here, I'm just gonna make a note that this implication is only false for a true statement going to a false statement. Otherwise, it's always going to be true. True to true, false to true, because you end up at true, and then false to false is true because you're establishing a false universe and then you're going to another false universe. So from here to here, and then the other way around, right? So false to true is true. True to false is false. False to true is true. False to true is also true. Okay. So, oh yeah, she's a bad girl. Let's see here if I can, I'm gonna need some more room. Okay, I'll start it down here. That's gonna get confusing. P and not Q. Now going the other way, not P or Q. So now I'm going from this column over to this column. So true to false is false. Hey, that doesn't work. Oh, maybe it's not a tautology. Didn't think about that as an option. Okay, so let me just get these columns straight. Oops, columns straight here. True to false. So that's the only time it gives a false statement. Yeah, did I do something? Did I muck this up somewhere? Can you go straight to the if and only if? Only if it's a tautology. Oh, like here. Feeling a little rusty here. You probably can. It's only going to be true if they're the same, right? Is that what you're thinking? And they're never the same. True, true. I think now I'm feeling rusty. You picked the question I was like, oh, that's easy. Guess not. I'm gonna go through and, hey, nice. October 28th. Please stay on the line. I've got them here. October 28th. Okay, looking at that first one, a little bit different. I did do that. P implies Q, if and only if not P and not Q. Church. I did jump straight to it. I think because I saw that they were the same, whereas in this case they're not. But you can just go straight to it. But I'm not feeling that confident anymore, so I'm gonna do the whole thing. A little bit more work. But you're allowed, yeah. So you would be allowed to go straight to it if you feel like you have it under control. Whereas I'm going to go from here, right, to here. So true to false is false. False to true is true. True to false is false. And true to false is false. And maybe what I'll do is I'll copy this just because I can. I'm going to do my best to show that this is from before. Because now they're not the same. So what I'll do is I'll go like this. Oops. They're not going back and forth to the same thing. So this one's false, 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 false. I wonder what the opposite of a tautology is. And all false there. Philology. Philology. Therefore, not a tautology, which would be all true. A tautology. I feel like that is something that we would have looked up. Tautology. Stealing that from Zach. I guess so. Because so here, this back and forth arrow is only going to be true if they're the same. But here, false is not the same as true. So that would give us a false. Here, false, false, false. I feel like we would have gotten there. So you could have, okay, so this, let's say this is optional and it's just me, or sorry, this is optional. That's just me being rusty and just trying to cover my bases, I guess. You could have gone straight to here because I'm bouncing back and forth between a false and a true, which will always be false. Right? Optional extra steps. I'll say that. False, 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 false. Feels good. I'm ready to lock it in. Any other problems you want me to go through? No problem. My pleasure. No problem. My pleasure. Now, hope you guys do well on the final. I think it's within your grasp. Raise you up. Yeah. Success. Thanks to you guys. It's been awesome. So fun. I know the vibe is going to be a little bit different for the final exam, but it's been really fun. So thank you. I'll stop this recording. I think probably done.